two things. One, test on Thursday. And next week, when we started, any questions about test on Thursday?
What chapters is it again?
It's 4, 5, and 6. First test was on chapters 2 and 3. 1-ish. 2 and 3, and then this one's 4, 5, 6.
So what's mainly gonna be on the test? Do you know what's mainly gonna be on the test that you're gonna have to focus on?
Now, if you look at, about the best way to judge what's gonna be on the test is look at test 1B that are posted online. Any other questions at the moment?
We need to have the kinetic energy formula memorized for the test, right?
No, kinetic energy is part of the last test, not part of the one you're doing on Thursday. All right, so 31st, and then, so I guess it's April 7th, April 5th. 12, 14. So master set 7 is due April 7th. And master set 8 due the following Tuesday. Yes. I did put that on the wrong one. Well, I guess it's due for them now. All right. So 4, 8, 4, 6. So master set 7, and then 4, 13, master set 8. There'll probably be the lab also due on the 13th. So pace yourselves accordingly. Fridays. School's out on Friday?
I think it's like Good Friday or something like that.
Except this is a state-run organization, we cannot have a religious holiday. It just coincidentally happens to be Good Friday. Actually, I think it says Good Friday or something like that. Separation of church and state, that's core. All right. All right, any questions before we just pick up where we left off? You'll look it up if we have Friday off?
It's closed, Good Friday, college closed,
Okay.
so. April 7th.
All right, we last left off. 3, 2, 4. All right, so we have a 5 kilogram mass here, we have a 4 kilogram mass here, heading towards each other. In a collision. Make it a perfectly elastic collision. So, one-dimensional, perfectly elastic collision. three different techniques to solve it. I am gonna go through all three techniques. I'm gonna sort of run through it, because this is stuff, what, not only are there several videos online, but we did this in class last time as well. So technique number one, we'll end up with a quadratic, but first off, it's gonna be a one-dimensional perfectly elastic collision. What are the two things that are considered in this collision?
Momentum.
All right, there's one. That's because we got a collision. As soon as I tell you that there's a collision, you should be thinking conservation of momentum. And because this is perfectly elastic, what's the other thing that's considered? More specifically?
Kinetic energy.
Yes, it's the kinetic brand. So we'll have two equations of motion here, or two equations, I should say, not equations of motion officially. Equations of motion refers to F equals ma. So momentum is conserved. What is the formula for momentum anyway? All right. And what's the formula for kinetic energy?
1/2 mv squared.
Yeah, you know, I didn't hear everybody there, but I heard enough people. Thank you. All right, so what does conservation mean in physics? If momentum is conserved, what does that mean? In some sense, let's see if we can express that a little bit more formally.
But not all of it's being used. But not all of it's being used.
Not all of it.
Being used.
Oh, not all of it's being used. I think you can make an argument either way on that one.
It's saved between the two forces.
Objects.
Object.
All right, I think we're dancing around it enough. Whatever we have to start with, we have this exact same amount. The total at the beginning is equal to total at the end. And the reason why we talk about being used, we're transferring it from one object to the other. And so, you know, is that used? That becomes a semantics issue. So a total momentum before the collision for this one is 15 units. Mass, oh, let's put some units in here too. So if the momentum of this one is 15 kilogram meters per second, what's the momentum of this one?
8.
Ooh, close.
Negative. Oh, negative.
Because as soon as I establish this is 15, I'm now saying that that is positive to the right. So that's negative, so negative is equal to 5A, actually what I did before was C and D. 5C plus 4D. Where C is the final velocity of the 5 kilogram mass, and D is the final velocity of the 4 kilogram mass. So I have 7 equals 5C plus 4D. I have one equation, two unknowns, that is not solvable yet. We are now left with the kinetic energy conservation. We have the formula right there. So I got 1/2 times 5 times 3 squared, plus 1/2 times 4 times 2 squared, equals 1/2 times 5 times C squared, plus 1/2 times 4 times D squared. And again, I'm trying to solve for C and D. I guess I didn't state that explicitly, but wanting to know what the velocities are after the collision is a classic. And this is a 5 and not an S. And going through the fancy math here, this is 8. And this is 2.5 times 9, which is 18, so 22.5. Equals 2.5 c squared plus 2d squared. Assuming I have not made a careless error. If I have made a careless error, somebody presumably will correct me, or we'll get a different answer when we solve it a different way. Your calculator agrees?
Yep.
Okay. So I have two equations, two unknowns. When I'm dealing with a linear and a quadratic equation, I guess my two techniques are I could substitution, which is what we're going to do. Technically, I could graph it. This is a parabola, actually. That would be something parabolic. Down here, this would be linear, and they're gonna meet at some point. Just meet at 2 points. So by substitution, divide by 4, divide by 5. I'm gonna divide by 5. One fewer decimal place. So I have 5c is equal to 7 minus 4d. C is equal to 1.4 minus 0.8d. Don't forget, when you're dividing by 5, you divide everything by 5. And now I plug into here, I get 30.5 is equal to 2.5 times 1.5 minus 0.8d squared plus 2d squared. We are now down to one equation and one unknown. And no, we would probably need a little bit of help here. 30.5 is equal to 2.5 times, well, that's squared. It's a binomial squared, so if you recall, a minus b squared is equal to a squared minus 2ab plus b squared. And it's not, as some students have claimed on tests and quizzes, it's not just the first one squared minus the second one squared. So 1.4 squared, I think is 1.96, minus 2 times 0.8 times 1.4, which would be 2.24. D plus 0.64 squared. Yeah, hoping someone will correct me. Actually, we will know if we did anything wrong when we get to the answer, because one of the answers will be they hadn't hit yet. And then distribute 2.5 times 1.96, something gonna be a little bit less than 5. So 4.4.
Yep.
All right, thank you. And then, so distributing here. Then 2.5 times 2.24.
Negative 5.6.
5.6. D plus and then a quarter of 0.64, or a quarter of 6.4. So 3, 2, 1, 5, 5.
1.6.
What is it?
1.6.
1.6? Okay. We have a quadratic equation, probably a quadratic formula. The one we did in class the other day could have been factored. This is not necessarily as easy a factor. And so let's combine like terms, get this thing set equal to 0. So I got my d squared terms right here. So 3.6 d squared. Then I have only one d term here, minus 5.6 d. And then subtract this from both sides, minus 20.
25.6.
Equals 0. We have it in classic ax squared plus bx plus c form, and so that equals 5.6 plus or minus the square root of 5.6 squared minus 4 times 3.6 times negative 25.6 over 2 times 3.6. So is the radical 8.8? Ooh, no. Radical 20?
Yeah.
Okay. So 5.6 plus or minus 20 over 7.2. Okay, 2 answers.
A lot of 5s into a 6.
Okay, so rounded off 3.5 per meters per second. Which of these is the correct answer for it having been in a collision?
3.5,
Why is the other one not the correct answer?
because it's negative.
Not wrong reason. I mean, ultimately, yeah, considering the, oh, well, actually, explore that one. Why is it being negative means it's not the right answer?
Because the 5 kilogram mass is going in the right direction, and since it has more momentum, it's going to make it go towards the right side, the positive direction.
So, because of what reason again?
Because the 5 kilogram mass has more momentum.
Ah, yes. If this is a negative solution, if this were correct, what would, after the collision, what would that tell you about the velocity of the 5 kilogram mass?
That would mean that, I'm not sure for that one.
Okay. I mean, you were, sorry about my quick dismissal of what you first said. I mean, your reasoning was right there. If the negative solution were correct after the collision, that means the 4 kilogram mass is still going to the left, still going to your left. Unless the objects pass through each other, the 5 kilogram would also have to be going to the left. Actually, it has to be going faster than -2. Or, I guess, fast as speed, faster than 2 meters per second to the left. When the total momentum, as Kano said, total momentum starts out being positive, therefore, there has to be something going in the positive direction. We need ultimately positive momentum. So if the 4 is still going to the left after the collision, 5 still has to be going to the left unless it somehow magically passes through. What's another reason why we automatically know this -2 is not correct? All right, well, let's carry on then. So, define, this is the value for D. I know that C is equal to 1.4 minus 0.8 times D. So therefore, in the first case, what does C equal?
I got negative 1.4.
1.4, repeating,
It just gave me a 1.4.
4, okay. And then in the second case? All right, so mathematically, these are the two solutions. What can you tell me about this second solution that Kano has rejected completely? But where have we seen this before? Yep, right there. Again, the advantage of this technique is that one of the solutions should be that they never actually hit. So this is the non-collision solution. However, they do collide because that was the problem. It's a perfectly elastic collision. It's implied that they do collide. Therefore, this one right here is the correct answer. So I'm gonna write that up here so we can always double check ourselves. So the velocity final 5 was negative 1.4 meters per second. And the other one, 3.5. Repeating, I think that 4's gotta be repeating. Meters per second. When you typed in your calculator, did you just type in 3.5?
Mhm.
Ah, okay. Now, on a test or quiz, I'm gonna look at that and go, yeah, that's close enough. On a lab, I would expect a little bit more precision, but this is not a lab exercise at the moment. Questions before we do this all over again, except a different technique? All right, technique number 2, we still need that one, so we'll get rid of that. All right, technique number 2, we got the relative speed of approach equals the relative speed of recession. In other words, from 4's point of view, how fast is 5 approaching? Well, from 4's point of view, 5 is approaching at 5 meters per second. 3 minus negative 2. That is the relative speed of approach. Relative speed of recession suddenly looks at it from the other point of view. So from 4's point of view, 5's coming at it at 5 meters per second. After the collision, how fast is 4 going away from 5's point of view? And so that will be D minus C. So the first one was, I guess, B minus A. A minus B. So we have this equation right here. From this, I can see that, actually, actually solving for D might make more sense here. D is equal to C plus 5. And we can plug into this equation. We've got several things in which to plug. Let's plug into this one right here. So I have 7 is equal to 5C plus 4 times C plus 5. So that's 5C plus 4C plus 20. Negative 13 is equal to 9C. C equals negative 13 ninths meters per second. And if you do that on a calculator, you'll get the negative 1.4 repeating. And then D, you just add 5. Ninths, which is 3 and 5 ninths, or 3.5 repeating. So technique number 2. And then questions on technique number 2? The advantage of technique number 2 is that you're not dealing with a quadratic. It's already been dealt with in this formula right here. The disadvantage is you don't get the immediate feedback of whether you, something like this, where in the first technique, we got the original problem as one of the answers. And then technique number 3. It's the reference frame. So we've got the 5 kilogram and the 4 kilogram. So in the lab frame, this is going 3 and this one's going negative 2. We need to shift out of this reference frame into the zero momentum frame. In other words, we need to solve the perfectly inelastic collision problem. Well, we start out with 7 units of momentum. Afterwards, in the zero momentum, in the perfectly inelastic collision problem, they stick together. So afterwards, it would be 9 times whatever their speed is. And so V is 7 ninths. So now I shift, minus 7 ninths, minus 7 ninths. So this becomes 20 ninths and negative 26 ninths. So this is the zero momentum frame. Nope, something's off. Because this is 25. Now the reason I knew something was off is I did a quick check. I know 5, it's zero momentum frame, so 5 times this, mass times velocity, plus mass times velocity should add up to 0. And I knew that 5 times 20 and 4 times 26 are not the same number. But now 5 times 20 is 100, 4 times negative 25 is negative 100. When you add them, you get 0, which is what we expect. And then the collision. Collide. Still in the zero momentum frame. In a perfectly elastic collision, all we do is we want to maintain the same kinetic energy and same momentum. Well, our momentum is 0, but we just switch signs. In this frame of reference, they just hit and they bounce back. Then we shift back. Plus 7 ninths, we just do the opposite of what we did before, plus 7 ninths. and we end up with, we're back in the lab frame. Negative 20 plus 7 is negative 13. And 25 plus 7 is 32. And lo and behold, that's what we had before. Are there questions about this technique? I know I zipped through this, but this is, again, what we did last Thursday. So now, I'm gonna give you your own problem that I want you to work on right now. You can feel free to talk to other people, this is not a quiz. It's a chance for you to practice. Of the 3 techniques, pick one. I don't care which one you do. Pick one and run with it. If you find that that technique ultimately doesn't work for you, pick one of the other ones. There's loads of practice about doing this. If nothing else, you can always pick your own numbers and solve it all 3 techniques and see if you get the same answer. I was hoping to pick one so that the answers are integers or at least simple fractions. Let's see. In class, last week, what masses did I pick for them? Did I give you?
4 and 10.
I gave you the 4 and 10. I have not done the 3 and 1. I guess not. All right, so. So 3 kilogram, going to the right at 4 meters per second. And 1 kilogram, going to the left at 6 meters per second. If I'm looking at my notes nicely here, I believe that the answers are integers.